Right, now the fundamental question is, does this computational rule give us solutions of that partial differential equation? There's two aspects to that. We need to establish consistency and stability. So recall that operator algebra empowers us to show that this is indeed consistent. So that's the first thing we do. And what we'll do is change some of these spatial derivatives into operators using the rules that we found earlier in theorem 4.4 was, namely that the centred derivative in centred difference in space is the same thing as 2 hyperbolic sine h d dx over 2. Now I've got a subscript on the difference operator x, and that denotes that that's a difference in space, because now we not only have a discretisation in space, but we've also got discretising in time, a lattice in time. So we'll denote operators that act in the time lattice with a subscript t, as on this shift operator e, subscript t being e to the tau dvdt, which is the time version of e to the h dvdx that we saw earlier. Alright, so using those operators, the computational rule is written like this. UJL plus 1 is just the shift in time by one amount tau, so UJL plus 1 is E in time UJL. The right hand side is UJL plus S times this second centred difference, which was, you recall, the delta x squared UJL. Now this equation is to be satisfied for all UJL everywhere across this grid, and so we can in essence factor out the UJLs and just do algebra on the operators. So our computational rule is equivalent to the operator equation. ET is 1 plus S delta x squared. Now, what does this mean in terms of derivatives? Well, the shift operator is e to the tau dvt, and delta x squared is the square of this, so that's 4 hyperbolic sine squared h dx over 2. In other words, the computational rule is, on taking logarithms and dividing by tau, dvdt is 1 over tau log 1 plus s for sine h squared h dx over 2. Now, to see whether it's consistent, we want to look at what happens as the grid spacing goes to 0. That's h getting smaller and smaller. So h is small, and so we look at a Taylor series of the right hand side in powers of h. Now it's a bit tedious to compute by hand, so I leave it to you to do some computer algebra to find the Taylor series of the right hand side, namely that it is, let me just copy from my notes here, 1 over tau s h squared dvdx squared plus s h to the 4th into 1/12 minus a half s dvdx to the 4th plus order h to the 6th. Alright, so you do some computer algebra, you get this result. What does it mean? Well, first thing to note, to remember, is what S is. S is k tau over h squared. So in other words, sh squared over tau is the same thing as k. So this is dvdt is big K dvdx squared plus, now sh to the 4th over tau and that's just kh squared. So there's kh squared into 1/12 minus a half s dx to the fourth plus other terms. Okay, so this is the operator equation. What it means is that this computational rule has an equivalent PDE, which is what you get by applying this to a function u. Namely, du by dt is k times uxx plus k h squared 1/12 minus a half s u four derivatives plus higher order terms. And at this stage we can now say, establish the consistency, because what do we see here? We see here it's the desired PDE, so that's good. And we see that the computational scheme does something slightly different to solving the PDE. It solves this. But the leading error, the leading difference, is this term. And that term has a coefficient of h squared in it. So it's of order h squared. But specifically, as the h goes to 0, this right-hand side, everything from here on goes to 0 because it all gets multiplied by h squared, giving that the computational rule is consistent with the desired PDE, and that establishes consistency.